Hi everyone, welcome to the bi-weekly MicroJIT meeting. Um, is there anything anyone has to discuss?
Well, I guess we should probably start with Harpreet first. She's been doing more work on trying to refactor how MicroJIT does linkages,
Yeah.
specifically trying to bridge the gap between MicroJIT and TR in that respect so that any change made to how TR handles its private or system linkages will be reflected in MicroJIT as well and won't trigger weird bugs or problems in testing.
Yeah. Okay, I can go first. Yeah. So my very straight question for today would be right now I'm working on, like as Scott said, we are working towards making the things common between the MicroJIT and the default compiler. So towards that end, uh, I have tried to utilize the properties from the TR. So that has been done. So currently I'm working on the left to right ordering. So for that, Daryl or if anyone has the answer for this. So at this point of time, what are the different types of linkages that we should work upon? Like till now, we were working only towards the private linkages. So there are some other like the system linkages, or I don't know if some others are there. So how, like, what should be our current focus on?
So the private linkages are the linkages that are used. It's essentially the linkage that we use for compiled Java methods in the full JIT. So it is a linkage that is optimized for JITted method to JITted method dispatches, but it does have provisions for JITted methods to call interpreted and interpreter to call the JIT. So if you are trying to come up with a linkage for the methods that for the MicroJIT, it would seem that the private linkage would be a good one to model it on, and obviously that's what you've been doing. The other linkages that are available are all related to calling native functions. So what we call system linkage is really um, whatever the sort of the C calling convention is on a particular platform, and it may vary by operating system. It may vary by architecture as well. But that is, if you ever need to call a native function from JITted code, that is the linkage that you would use, system linkage. And by extension, the JIT also uses, it also has an optimized path to do Java native interface dispatches, so JNI dispatches. And a JNI dispatch is essentially, we're calling a JNI method, which is essentially a system linkage call, but it's got some extra arguments stuffed in, or it has some extra requirements that the Java native interface requires. So we have, for example, the first argument has to be an environment pointer, so we have to pass the VM thread as the first argument. So it uses system linkage, but we change it in such a way that we insert arguments or we package the parameters in such a way to abide by that. I'm not sure you have to worry about that yet. JNI linkage. I think you just need to focus on private linkage to begin with
Okay.
for method to method copies. So did
Right.
that answer your question?
Yeah, so you mean that currently we are working towards compiling the methods. So our foremost priority would be, like, for the time being, it's we should do the private linkages, right?
you should do you need some you need some kind of a calling convention for micro-JITted methods to micro-JITted methods, and I think the effort that you've put in so far has been to reuse a lot of the similar calling convention that we use on the full JIT. So yes, I think continuing on that path where you are incorporating private linkage, as we call it, is the path you should be on.
So when you say full JIT, so that means the Testarossa, right?
Yes.
Oh,
yes.
Okay. Okay. And one more thing that when I'm working towards the left to right or maybe the right to left ordering, so those are set in somewhere in the property, right? In the properties structure. So, like, do we pass? Where do we call it from externally? I mean, is there some parameter linked to that in the XJIT options, or
Sorry, where do you call what?
I mean, I just need to understand that currently I will be executing, I will be compiling a certain, say, a basic integer addition with the MicroJIT. Then the ordering of the arguments would be the default, that is the left to right. So what should I change? How should I test if I need to test the right to left ordering? How would I would certainly change the order in the Java method while I am calling like integer a comma integer b. So I would do the int b comma int a. So that is how I would test, and then the system should work. The ordering should work after I implement.
I'm not sure if I followed all of that, but if your general question is what do you need to do to implement either a left to right or a right to left linkage, and then how do I test the thing that I have just implemented? Is that generally what your question is?
Yeah, that's the question. That how do I test? How do I see that that this is working fine now after I have written some piece of code? That's my question. You're right.
Okay, well, I mean, you would, I mean, just in terms, I think I had mentioned this to you on Slack. I think was it a couple of weeks ago, something like that, about how even if you went, so the basic thing that you would have to do is to change the property in the linkage properties to basically say this linkage is either left to right or right to left, and then you would have to add some logic somewhere to make sure that when you're passing parameters, they get passed in left to right order. And then, like, so when you're assigning registers or you're assigning a stack slot or pushing them onto the stack in order to you have to go in a left to right or a right to left order. And then on the call side, in the prologue, you've got to make sure that you're receiving those arguments in the right order, either left to right or right to left. And I think, if I remember correctly, I think we found a couple of places in the code that where we do the left to right, or where we do that. Now, I also pointed out that because we've been doing it pretty much only one way for the past 20 years, if not more than 20 years, we may have gotten a bit lazy in the code and omitted the checks for, am I going left to right or right to left, right? So for example, on x86, we may have been going left to right for 21 years now, and there may be places in the code that don't check for left to right or right to left where they should. And so there may be some examples of places that do not work if you suddenly switch the ordering. I can't tell you off the top of my head where those places are, because it would almost just be a debugging exercise at that point to figure that out. But I'm just, I guess, maybe just warning you that don't expect the code to be 100% correct. There may be some problems there. So yeah, so those places that I think I pointed at you to in Slack that I don't recall off the top of my head here, but you can maybe go look at those places. Now, in
Yeah.
terms of how to test it, I mean, obviously, I think one of the best ways of testing it is you write an application or a very simple unit test that you're basically passing, a number of arguments to a method, and that method is expecting things to arrive in a certain order. So so
Right.
if you pass 10 parameters to some function,
Yeah.
and that function receives them in the opposite order that you're expecting them, then obviously there's something wrong with the way that you had passed them. Sorry, it's either wrong with the way you pass them or wrong with the way that you receive them. So that would be a fairly straightforward way of determining whether or not you are passing things in the right order. Now, I would encourage you, when you're doing testing, is to exercise combinations of things. So you want to mix floating point and integers, for example, on your arguments. You want to have some very long, I don't say very long. You want to have some long argument. You want to have some functions whose signature have got a very large number of parameters, because you want to test the case where you're passing things in registers. When you run out of registers, you have to start passing them on the stack. So you want to exercise that case. You want to call things that have very few parameters as well, to make sure that, okay, everything here I'm expecting to pass in registers. So how does that work? If you're testing things on 32-bit, which I don't know if you are or not, but if the MicroJIT is working on 32-bit, some things get passed as pairs of registers. So for example, we pass a 64-bit long, as a pair of 32-bit registers. So you'd want to make sure that you use long in that signature as well. And then you also want to look to see that the long itself got passed in the right order, like those registers got passed in the right order. What else could you do? But yeah, I mean, I think just executing a call and checking to see whether or not the thing that you passed was received in the order that you expected might be the easiest thing to do. Do you have to do anything with the return? No, that doesn't really affect left to right or right to left. But I mean, obviously, as part of any linkage unit testing, you want to test returning the various types of various types. So integers, floats, addresses, returning nothing. That's another thing. Now the other thing, not to overly keep complicating things. So since we're talking about private linkage, and we're talking about a JITted method calling something, there are, at least in the full JIT, you can actually end up calling different things with private linkage. So you could in fact be calling a JITted method, but you could also be calling an interpreted method, right? So from the perspective of in the full JIT, like I said early on, the linkage is optimized to expect that you're calling another JITted method. So it's from a JITted method to a JITted method. And if you are not calling a JITted method, so an interpreted method, the linkage doesn't care about that. It expects that something else is going to happen to modify the linkage as appropriate, modify the arguments as appropriate, to get them in the order that the interpreter would expect, right? So in this particular case, if you're calling from the JIT, if you're from the JITted method, if you're calling a method that actually is interpreted, what that essentially means is that we have to take any registers that are passed, any arguments that are passed in registers, and store them onto the stack in the right order that they need to be in. So So there is actually what that means is that we don't actually call an interpreted method directly. We would end up calling what we call a thunk that knows how to convert for a particular signature, it knows how to convert the JIT calling convention into and store those registers onto the stack in the right order, and then it allows the interpreter to go away. So what I'm saying there, though, is that in any testing that you do, you have to make sure that you have a mix of compiled targets and interpreted targets as well. And not just interpreted, but also things like if you have the ability to call an INL, like an interpreter native, which you might, then you want to make sure that those things are in the mix as well. So I guess one question that I have for you is, have you thought about like, is this going to be a mixed mode JIT? Like, you have the ability to call an interpreted method still, or is it all compiled?
No, right now it's all compiled.
Okay.
Yeah.
Actually,
So,
I would jump in here and say we can, because the way we do our calling, because currently the only invoke bytecode we support is invoke static. And we're still debugging things relative to that. There's something right now going wrong without getting into the details. There's something in our benchmark suite that's causing object hash code to return bad values, and that causes the whole VM to crash. But we do use the interpreter or the x86, because right now we only support 64-bit x86, and we set everything up where we pass in the method pointer into RDI and jump to the invoke interpreter special and static glue, which I believe is that thing that does the hook that thunk that jumps into doing the interpreter if it's interpreted, and patches the call or the jump instruction, or the call instruction rather, if it isn't if it is JITted, and then you don't have to go through the interpreter thunk anymore.
Right, and the thunk, if I'm not mistaken, I think there's some code in that. Not the thunk. So in the full JIT, we call that there's what we call a snippet to do that dispatch. Like an interpreted dispatch snippet. And in that snippet, which actually lives in the JITted code, I believe there is code there that will spill the register arguments onto the stack before it calls that dispatch to interpreter. Because otherwise, no one is going to store the JITted arguments onto the stack. Do you know what I mean?
Yes, but now I'm wondering if maybe that's the source of my problem, because I think, though I don't know how it would have worked beforehand if this was the case, I think that we might be doing something wrong there, because we don't store that in a snippet, we store that in line. And if the patch is expecting to patch the call to the snippet, then there would be some extra argument moving that would happen. But we have definitely tested things where we call JITted code and where we call interpreted code that both work.
Okay, in the full JIT, and that's really only where my experience is. I believe you're right that if we're calling an interpreted method, like a static interpreted method, that glue code is going to be looking for the call to the snippet and patching that to call the JITted method. But it is the snippet that is responsible for backspilling the arguments onto the stack. I was just trying to see if I could find that code just to confirm that. But if I remember correctly,
if I remember correctly, One of them is an x86 JIT helpers. Although it's a NASM file, so maybe the name of that's wrong, but it's an x86 something helpers, or helper something. It's a NASM file, and it has a bunch of stuff in there relative to the JIT calling into the interpreter, and it's all those hooks. And there was a time way back when we were first doing the PR for MicroJIT where we had made changes to that to support MicroJIT having that extra 2 field before we switched over to using GCR and having only 1 extra field. So I'll see if I can help you find that.
I'm looking at this. Give me a sec. I'm just trying to bring up the file in the browser.
That's okay.
Where am I? Snippet body.
I found it here. It's runtime compiler x runtime x86 unresolveds or unresolveds.nasm.
Right. Okay. So that's one layer below what I'm looking for at this
Okay.
point. Let me just. Way too many windows open here. I'm looking for my WebEx one so I can screen share it. To find. There it is. You see do you see some code?
Yeah.
Okay. So this is in xcogen call snippet.cpp. So we emit these for like unresolved like for unresolved statics or for when we know we're calling the interpreter. Like at compile time, I can tell the target is not compiled yet, so therefore I have to lay down some code that's going to take me to the interpreter body. So what this code is essentially doing is laying down some out-of-line code that's going to take us into the interpreter. But one of the first thing it has to do here is, if you can see this blob of code here, it's got on 64-bit, we have to backspill the linkage register arguments to the stack, right? So this is the code here that'll walk through the signature of the method that you're calling, and based on the linkage, which in this case is private linkage, it's going to store the arguments from, if they're passed in a register, into the appropriate spot on the stack so that the interpreter so we can just dispatch to the interpreter. So it'll do that, and then you should see code that looks like this, essentially. It's going to have, I thought we had loaded up the RAM method into RDI. Don't we do that?
I assume we do that based off of what I'm reading here in the unresolves, because in the interpreter unresolved static glue,
Yes.
it calls or it pops EDI. Or
Right.
pops
So
something into EDI from the backspill.
Right. So actually, that's what the comment here is saying, kind of too. So move RDI. This code here will be replaced with move RDI, which will jump us into interpreter static and special glue probably in PIC Builder. I think that's where that is. But So this code here is for the unresolved case. I think there's a case for where it is resolved already. Yes. Sorry, that's the one I'm thinking off of my head. This is the simpler case. When the method is resolved, the method you resolve, it's basically just load, after we've stored the stuff onto the stack, we basically load the RAM method into RDI and then call interpreter static and special glue. And it's basically calling, that'll just take us right into the interpreter. But it'll, through that path is what you were looking at, where we check, oh, is the target actually compiled? And if the target now is compiled, then it'll go and patch the instruction that called the snippet to basically call the compiled method instead. Does that make sense? But if you don't have any code that is storing the arguments onto the stack like the interpreter would expect, then you're in trouble. You need something that's gonna do that. And that might almost certainly be the source of your problem, if you're able to call interpreted methods from compiled methods.
So we are very likely calling interpreted methods from compiled methods, and that sounds like it might be the source of my problem. Although I also think that I'm not calling necessarily, I may have accidentally gotten something that mostly works by calling the wrong thing, because what I'm calling doesn't actually, by the look of this, do the patch, or maybe it does. The interpreter static and special glue, it says the function is a back patching routine for interpreter calls to static methods that have recently been compiled, patches the call site and the code cache of an interpreter call snippet, so that future executions will invoke the compiled method instead. But it looks like it just checks if the thing's been compiled, and if it hasn't been compiled, it just jumps to the J2I transition. And if it has been compiled, from what I'm reading here, it looks like it is just patching the jump, that like the call that brought it to interpreter static and special glue, because we don't actually support calling things that haven't been resolved yet.
Okay, so do you call, so question is, do you call interpreter static and special glue, or do you jump to it? So if you see the code here, the way we get into the snippet is through a call. So it records the address in the mainline code on the stack. But when we get into the snippet here, we don't do another call, we do a jump. So the return address that's on the stack at this point is the return address in the mainline code. So any patching that gets done by interpreter static and special glue or anything underneath it is going to patch the thing in the mainline code. If this was another call here, you'd have an extra thing on the stack, and there'll be two problems with that. One is you're going to be patching this, which is not the right thing, and you're also changing the shape of the frame here, and the stack walker is not going to know anything about this extra thing that lives on the stack. You're going to have to teach the stack walker about it.
Yeah, and we definitely wanted to get away from doing anything to the stack walker.
So if you're following this convention that we're doing in the full JIT, then yeah, you're going to need a call from your mainline code to something that is going to take you into the interpreter, and expect that call to be patched by the interpreter.
Okay, so it looks like what we're doing is basically everything that usually would go in that snippet is being instead pasted in the main line of the JITted code, and we call that interpreter static and special glue instead of jumping to it. So we don't call the snippet, we call the interpreter static and special glue directly, which means we do have a mismatch very likely on the frame. So that's probably the source of all of my strife at the moment.
It's the fact that probably one of them. It'll look a little bit. You're doing this in mainline code. Is sorry, I don't remember off the top of my head. Is RDI one of the linkage registers in private linkage?
I don't believe
I don't think
that
so.
it
It
is
can't
off the
be.
top of my head.
I don't remember off the top of my head either. But
Actually, wait, I have
you,
that in a comment
it-
up here somewhere above. So let me go to that and see if I can find it, because I have a big pasted comment that gives the entire call stack and everything else. Okay, parameters passed by the caller, return address, RSP. Wait, no, that's the wrong block comment. I need the block comment in the linkage. I think it's in HPP. Yes, it is. Okay. x86-64 architecture, little endian, return addresses on the stack. Argument registers are RAX, RSI, RDX, and RCX. Preserved registers are RBX and 9 through 15. Virtual tables in R8. Receivers in RAX, and the return value registers are RAX and XMM0.
okay, so RDI is volatile then.
Yeah.
Okay. All right. So all right. Okay. Yeah. I mean, you might be able to get what you have working, but it is not a very optimal. It is not a very optimized sequence at all. Like once, like if you did turn this jump into a call to get you in here, and then you went and you patched this thing up. I'm not even sure what that would.
I think it would end up being an
Like,
extra move.
You would still have to have all that logic up here. Like you would still have all this code. Like for any dispatch, you would then have to store all these arguments onto the stack, which you don't want, because that's only needed in the event that you're calling the interpreter. You do all these stores, and then you would do a load of RDI, and then you do a call. Like you should be doing this out of line if you're expecting, like in a snippet, if you're expecting to get any kind of performance out of this. I mean, functionally it may work, but it's just
it's going to add a bunch
very
of
good
extra stuff.
It's going to add bloat to your code, but yeah, it's just going to look it's not an efficient piece of code at all.
Yeah.
So I encourage you to look at CoGen call snippet to see how we do this.
Okay.
And this, again, this will also give you a clue as to what all this other underlying logic in interpreter stack is expecting. I think on x86 we've done a decent job documenting like the shape of the stack expected at various points, if I remember correctly.
If I think we had a discussion about this before where that wasn't the case, but somebody was working on that, so I think that may have happened in the meantime. And then, so if you have that information, then I would absolutely love to get a pointer to it. Because the last I had of that was back when that documentation was all in like a text file that someone had written by hand.
No, I don't. No, that's not what I meant. Pick builder. I just meant things like this.
Okay, yeah. All right.
When you're calling one of these guys, this is what it's expecting to see on the stack and where the return address is and all that. So if you can, I think these are still relatively current, so that if you, if you can match, you make sure that the stack is matched like this, then you should be go. If I'm trying to think, I don't think you can change if the MicroJIT is supposed to coexist with the full JIT. I don't think you can change these properties, but if it was a completely independent implementation, then you could. I can't remember exactly where they are, but there's a file that basically it's all ifdefs. You can change the shape of these different things, but again, you're now getting into manipulating the stack walker. So that's buyer beware there.
Yeah, we definitely want to avoid that.
What was the name of that?
Which one were you looking for? The one for calling a.
Yeah, I don't.
It's in. Which one are you in right now? Because I can't see that because it says viewing. You're in Pick Builder. Okay, that's not the one that I was in. I was in x86 Unresolved, which is runtime. Yeah, it's in the same spot. Runtime compiler x runtime.
Okay, so it's.
And it does also have some documentation for most of these things. Next to every instruction, more or less, there's a comment that says why it's there and what it does. There's comments intermixed in the code. And the one that right now we're using is interpreter, static, and special glue. And it has some notes there. The RAM method is an RDI entry. It was loaded by the preceding instruction. This runtime code uses the JIT linkage registers as volatile registers and hence does not preserve them. This is because the eventual dispatch path will be through the interpreter, which reads the parameters from the stack. The backspilling has already occurred at this point.
Yeah.
It's a pretty short piece of code. It just tests to see if it's been compiled by checking the method not compiled bit. If that's 0, if that's non-zero, it just jumps to the interpreter stuff. So it's more likely that we were getting the interpreter stuff right and messing up the compiled stuff.
I don't know how you would have gotten the interpreter stuff right if you didn't do anything with the arguments.
Yeah. Well, I see. Like it's more like the other way around. Like we're always going through the path that assumes that we're going to invoke an interpreted method, and then the patch happens over the jump to interpreter, static, and special glue. Because we call it instead of jump it, if we find that the thing we're trying to compile or we're trying to invoke has been compiled already.
Yeah, I think I understand that. I guess maybe I think we're talking about two different problems here, right?
Yeah.
One is that problem about figuring out, am I actually calling it a compiled or an interpreted method? And if I'm calling a compiled method, I need to patch my caller so that future invocations is going to go through the compiled body. That's one problem that may or may not be working. But the other problem it seems like you're missing is the code to actually marshal the arguments from the registers onto the stack. Because it doesn't matter, because if you get that wrong, or if you have that code completely missing, then you're just going to get completely random behavior from the you're just passing garbage in to the interpreted method, and it's almost for sure going to crash or do something bad at some point.
I think so I've got a section here for generating the argument move for a static method, and I believe that includes putting things on the stack.
Okay.
No, hold on. We did encounter that problem. But then we did, instead of doing something about it, we just decided that we would push that off to a to-do and check to see if the parameter count goes above what can fit on the stack can fit in registers. So if we pass that 4 register parameters thing, then we failed to compile the method that is invoking the other method. So the compilee that we're trying to compile, we just return can't compile this and then move on.
I don't think the count unless you're not passing any parameters at all. I think that's the only case that you can do that. If you're passing even just one parameter, it has to be stored on the stack. If you're passing 10 parameters, they all have to be passed onto the stack. The only way that what you just said works is if you're calling a method that doesn't have any arguments.
I think, okay, no, we do add it to the stack. All right, so I would share this code on screen, but it is also fairly, it's very much hacked the bone to get something to work kind of code. So what we do is we loop over the parameters. Well, we first check to make sure that we don't actually have to worry about things being on the stack for the parameters of the method we're calling. Then once we've gotten around that bug, that special case that we haven't fixed yet, we check the entries, and then for every entry, we figure out which argument it is, whether it's the first, second, third, or fourth argument. Then we check what type it is in the type string of the method we're calling, and then based off of the position it's in and the type of it, we call a specific template for moving that argument onto the stack for the call. Which we don't actually clear the registers that they were in before. So if we end up jumping or calling directly the the method that after it's been JITted, it has all the arguments in the place it needs, and the stack just looks weird. And in the opposite case, if there's an interpreted method, things are on the stack, so it ends up working. But again, like you said, it needs to all be fixed. It should not. It should all go through the snippet thing and do things the way that TR is doing it to prevent those issues and to get the performance gain out of patching it in the first place.
Okay. Yep.
I'm gonna add that in as a to-do above this. To-do C commit snippet code and redo this to use snippets. All right, that's that. Now, very quickly, well, I say very quickly, but we have no control over that. There was something I wanted to pick your brain about while we had you on the call as well. So right now, what I'm working on, I'm getting kind of to the point where the current project in MicroJIT that I'm working on, or sub-project, whatever you want to call it, for profiling instruction omission, is getting towards the end of that project. We're hoping to have that done sometime the summer and have one, if not two, papers on it. And then the next thing on my list to do is I want to look at local optimizations, things like peepholes or common sets of instructions that pop up in terms of bytecodes that pop up together, where a template could be made to match more than one bytecode to get an improvement. There's some people who've done that before in places where their compiler was a template-based compiler, but they didn't have another JIT that came afterwards that did more optimizations. They just had the template-based compiler. So research-wise, there's an interesting problem there of how much optimization is too much optimization for a warm-up compiler or a baseline compiler. But the technical problem there is I would need to figure out what kind of peephole optimizations we could reasonably get away with. And I was told by Marius that there's some examples in CodeGen of peephole optimizations that you guys do, and that you would be a good person to ask about that. So could you tell me a little bit about how TR is currently doing peephole optimizations, like a store after a load, so that all you have to do is, or sorry, a load after a store, so that rather than, spill it or spilling something off the stack and then loading it back on, you're just, saving it in its place in memory.
Yeah, actually, x86 doesn't really do many peephole optimizations. I think that the other architectures have looked. I think the kinds of peephole optimizations that are done on other architectures have really been to look for at the instruction level to see if there's certain combinations of instructions that can either be eliminated or transformed into some other pattern. The kinds of things that you've been describing so far, we really leave up to the earlier optimization passes for taking care of like things like local common subexpression elimination or constant propagation, things like that. And even simplifier. There's a whole simplifier that runs to look for opportunities like that. The backends themselves don't really operate at that level. Now, the simplifier, I believe, is now a requirement for the backend. Even at no-opt, we have to run the simplifier. It does do some cleanup on some kinds of code or puts trees in the right order for the backend to operate the way that it does. So I'm not sure if that's what Marius had in mind, but maybe looking at the simplifier is what you want to do. And the way that works is depending on the opcode, the IL opcode, this is now speaking in terms of the full JIT, it's a fairly localized a localized bit of optimization, but depending upon what the IL opcode is, let's say it's an add, it will look to see if there are some fairly simple transformations that it can do at the tree level in order to simplify that particular operation. So just as an example, I'm not sure how often this would occur, but just an example, if you're doing things like an add plus a 0, right? Or sorry, an add of some variable plus a 0, it'll get rid of the add and just replace it with a load of the variable, right? Because the 0 has no effect. Same thing with a multiplication by a 0, it'll just replace that whole thing with the 0. So fairly simple, very local patterns that it's looking for, and it simply replaces some set of IL with another set of IL. So if you look through the simplifier common and the simplifier.cpp and the optimizer, you'll sort of see all those kinds of optimizations. So there may be similar patterns that you can recognize at the bytecode level.
Okay, so is that the sequential store simplifier?
No, nope. That's a more advanced kind of thing. It's I'm right here. I think it's probably in OMR actually. It's not in OpenJ9. I'm gonna guess this is gonna work. Blood master, compiler, optimizer. Cross your fingers. Oh. Oh, of course, it's a Calypso one. Optimizer. There are the word simplifier is used in a number of places here, but here these are the ones I'm talking about. The simplifier is probably where most of the work is, but
Oh, sorry.
yeah, it's basically a bunch of these handlers. Actually, where's the table? Where's the table? There's the enum. Where's the actual? Oh, simplifier table.hpp. It's basically this massive table of OMR simplifier table.enum. Okay. And for each IL opcode, there's like a function that gets called, a handler function for that IL opcode. That's what really drives it. Is that all that's in here? Oh, include IL opcodes. Yeah, so it's basically including it's redefining the opcode macro and then including the opcode enum. So what it's really saying is that for each of what this is a relatively new pattern that we're using, but what it's saying is that for each IL opcode in that enum, you're going to find a method, a handler method called whatever that opcode name is, appended with simplifier handler. So like IA or a load I simplifier handler. We should find one of those. And I think up here, these are all the names that would get mapped. It would map to all these things. So let me just say I a load, or sorry, a load I simplifier handler. So like that. So if a load I is the name of the opcode, you append simplifier handler to it. It's pound-defined to be an indirect load simplifier. So we would find that in Omar simplifier.cpp, I believe. What was the name of it? Indirect load.
Indirect,
load, yeah. Load simp or something like it, or handler.
It maybe it's an OMR simplifier handler.
Maybe, yeah, that would make more sense, wouldn't it? Yes. Come on. Big file, I guess. 15,000, yeah. Load simplifier, is this the handler? I guess. Wow, this is slow. Okay, so yeah, so for indirect load, this is the thing that's going to get called. Actually, let me look for something that's more. Is there an arithmetic one? Add, or that's, sorry. I usually use an editor for this. Come on.
Yeah, and I don't know what that new feature they added to GitHub has done for performance on the browser side of it either. I forget what that thing's called now. The thing that parses code and tries to come up with suggestions for things. I don't know if that thing's running when you open these things or not.
Okay, so I add simplifier. Okay. So essentially, it's going to be looking for things like, oh, are you a constant plus a constant, right? So if you are, I'm going to fold you away. I'll do the addition at compile time and replace you with a constant, right?
Okay.
What can we do?
And this is still all looking at the IL, so I'd have to try and do something clever with tables and things to avoid using an IL and do it all in a single pass.
Right. I mean, this is like this is an IAD of the first child as a neg, and is it trying to convert it into a subtract or something like that? But yeah, so I'm not sure if this is what you had in mind of the kinds of people optimizations, or if you were looking more at the oh, look, we had just stored into some auto A, and then the next thing was I loaded from auto A, right?
Yeah.
And then, so we don't do that kind of, even, I don't think even the simplifier would do that, because we do rely on other optimizations to do that, like local CSC or something like that. So that is kind of a new sort of people thing that you would have to implement, I think.
Yeah. So the one of the ones we were looking at was specifically, and it was suggested to me by someone at CastCon. I think it was Bill Hayes, and he said that if you have very frequently compilers will emit things like store this and then load it. And I actually looked at some of the tests and even some of the basic tests we write for testing our bytecodes, where we're not handcrafting the assembly, do those things where it says, okay, store this value and then load it again. And what I'm looking for in that context is the bytecode template we have for store will pop it off of a stack that we use for computation. We do stack based instead of register based. So because of that, because we don't have a register allocator or any of those things, and we are, moving a value from memory into a register and then into another memory location as part of storing, and then popping that value off, the entire load operation could be completely removed. And we could just
Yes.
update the stack pointer, or even just not pop the, not add to the stack pointer in the first place, and we'd be fine, right? So
Yep.
then we could turn that pair of, I store, I load into not only a shorter piece of code than we would have gotten before, but an even shorter piece of code than just an I store.
Yep.
And those are the kind of optimizations I'm looking for. Things where it's like, okay, it's very popular for someone to say have a low, I think it's I const 1 or something like that, to load constant 1 and then add it to something, because that's going to be your I++ operation in a for loop or something along those lines, right?
Right.
Or
So,
maybe it'll be smart and do an increment for that, but
yeah, so you'd have to find the right place to insert that in your backend where you can do that kind of people look ahead. Like if you're doing this all in one pass, then obviously when you're generating code for your store, you're going to have to look ahead to see is the next operation going to be a load, and is it a load from the same thing that you're storing, and is there something you can avoid here? So yeah, depending on how things are implemented, you're gonna have to look at where the best place is. So
yeah, I'm thinking we're going to end up doing something like that, like maybe inside the generate body statement that iterates over all the bytecodes, and we have a big switch statement for each bytecode that we add support for, and every time we add a new bytecode, a new case gets added to this switch statement. I think that thing is going to end up getting kind of large, and it might need to get moved to its own file. And then inside that, I'm probably just going to have helper functions below for, because we already use those for some of the larger templates like generate, invoke static, and stuff like that.
yeah,
So I'll probably in there have helper methods to just, generate the load, and then or generate I store. And when we do that, just check, pass the bytecode iterator and check, is the next thing a load? And if so, call this other thing.
Okay. Depending on how complex the code becomes, the compiler code becomes, you may, and depending on the cost of it as well, you may have to add a separate. It may be better just to add a separate pass that does p-polling, and then you do your code generation after that. That just to keep things less complex, to try to do it all in one. Just so you know, I have another call I have to start at 4:30. So if there's,
Yeah.
maybe we can wrap up in a minute.
Yeah, we can probably wrap it up here now, unless you have anything else you wanted to ask quickly, Harpreet.
No.
All right. Well, thank you very much,
Okay.
Daryl. That has been incredibly helpful. As always, it's lovely to have all of you guys here on the call whenever we do this kind of stuff. It generates a lot of good discussion and is very helpful for us getting through these kinds of bugs. Finding bugs with the invoke static early like this kind of helps us get this moving along faster. Hopefully sometime soon we'll have a fully updated PR with profiling support and even more bytecodes implemented. So thank you guys very much for all your help and for hosting these meetings.
Okay, no problem.
No
Anytime.
problem. All right, I'm going to stop recording.
Thanks.
Thank you.
I'm gonna drop now.